Swayam Prabha. Digital India. Educated India.
Good afternoon, everybody. Today I am going to start another module of this advances in welding and joining technologies, that is micro joining and nano joining. This is the module 5. So in this module I will try to demonstrate different micro joining and nano joining technologies that have been developed recently. And this micro joining and nano joining is significant specifically in today's industry because of the minimization of the product size, specifically their geometric size, their applicability, and with the development of the different devices like micro devices and nano devices. So that type of devices, the joining technology is very much significant. Micro joining and nano joining is nothing but the reduced form of the conventional joining processes, but we need to use the conventional technology and different perspective for specifically micro joining processes and nano joining processes. Although the nano joining processes is still developing, but to some extent the different micro joining technologies has been developed, specifically the electronics industry and some other medical devices. But nanogenic technology is still a very new technology, and it is maybe applicable in case of nano electronics or maybe different nano devices. So this module will try to focus on the different aspects of the micro joining and nano joining technologies, their basic mechanisms. More or less it is almost same as conventional welding processes, but there is some difference exists from the conventional joining technologies. So let us look into that. All the different micro joining and nano joining technologies exist in the current perspective, that means depending upon the current applications. So first I will try to cover the fundamentals of the fusion micro welding processes. Although the basic features of the fusion welding is, we have already known this phenomena, but specifically this fusion micro welding, in what aspect we can apply in case of micro scale processes. Second, different micro electronics wire bonding we will try to discuss, because nowadays the electronics industry, lot of joining processes are involved in this industry. Then bonding using nanoparticles we will try to cover, and then we will be covering the laser micro welding processes, which is laser source or maybe laser welding. It is known to us, or we have the idea about the different laser welding technology, but how this laser can be used in the micro scale application, that we will try to focus on this module. Next, electron beam micro welding. So although we know that electron beam normally we use when there is a need of high depth of penetration, specifically high thickness material, but this electron beam can also be applicable for the micro scale welding processes. But in this case we need to use this source of the electron beam in different way. We will try to discuss these aspects. Next, resistance micro welding and plastic micro welding. We will try to discuss that plastic micro welding, specifically the micro welding application where we use the non-metals category. Then micro joining of the medical components and devices, which is very significant part of this module, because lot of application we found out in the medical devices and medical components. And then we will try to focus on the advances in the laser micro welding processes and very specific and at the same time what are the recent advancement happens in other micro welding processes, since this course is related to the advances in welding and joining technologies. And finally, we will discuss that development of different nano joining technologies. Although this field is very new, but perhaps there exists or there is some development in that direction. So, we will try to focus on this thing. So, looking into all these aspects, first we will focus on the micro welding processes, and then nano joining or different nano joining processes. So, if we see that in the picture right hand side here, if you see that first picture, that microplasma arc welding process, and second next two pictures we see that macrograph of laser welding process. Now, if we see that what are the difference in these two cases, in microplasma arc welding process, if we see the dimension of the fusion zone or size is different from the laser welding processes. Of course, all these cases the materials are same. So, all these cases is what we have done, we have tried to join two different sheets of titanium alloy. So, grade 5 alloy. So, that titanium alloy is formed in the form of butt welding configuration, and we use the different sources. One cases we use the plasma source, another cases we use the laser as a heat source, but we can find out there is a significant difference of the shape and size of the fusion zone. So, this is possible because the concentrated of the heat in these two cases are different, and that depends on the different welding technologies. First case, it is microplasma arc, creation of the arc, specifically constricted arc as compared to the GTAW or gas tunnel arc welding process, and second case we use the laser as a heat source. But this can be considered as a micro scale welding processes because the sheet thickness in this case is around 0.5 millimeter, or we can say the 500 micrometer. But if you see the welding and joining of the metals and non-metals in a smaller scale can be considered as a micro joining processes, simply downscaling of the conventional welding processes, but it faces lot of challenges with respect to the different aspects, because only because of the minimization of the component. If you see that when try to reduce the thickness of a sheet which we supposed to join by any fusion welding or maybe other welding processes, and then the specifically the distortion becomes a very much problem when you try to reduce the thickness. So, this is one aspect, and at the same time the micro joining can also be possible to develop under the microscope, because the manual handling of all these components is really difficult when there is a reduced thick signal. For example, if we try to handle maybe 100 micrometer or 0.1 millimeter sheet thickness, it is very difficult to put, or maybe less than that, it is nearly impossible to put the manually and conduct manually, and at the same time to conduct some welding processes. So, in this case it is better option to put the development of the any micro welding or micro joining processes under the microscope. But even if we further reduce the size of the geometry of a sample, then it is possible to, that means up to the nano scale, then it is possible to do also nano joining. But definitely when you try to develop some nano joining technology, the handling of these samples probably not possible using the a simple automatic system. Probably piezoelectric manipulator we can use to handle the samples for nano welding processes. So, these are the typical maybe we can say characteristics of the micro welding processes that we can differentiate this process as compared to the conventional welding process. Now, if we see the another figure right hand side, the bottom figure, if you see, it shows that joining of the two carbon nanotubes. Here what we can do, we can simply placing two different nanotube, and if we very precisely apply the heat source at this joint, probably it is possible to do the joining of these two nanotubes. So this type of joining, we can say that there is a happening of the nano joining, but it's a, can imagine that how precisely it is necessary to control the nano joining process. Now what is definition of the micro joining or nano joining processes? If we see that before that actually the joining means we understand the welding, brazing, soldering, bonding all together can be considered as a joining process, and specifically welding maybe when we try to fuse the two material, and in general if we reach the melting point temperature, and after melting when the solidification occurs between the materials and it's come back to the room temperature, then that type of joining we can say that is called, in specific, that is called the welding. In general we can say like this. Also there may be possible the mechanical joining, for example fastening, riveting, crimping, also that is also comes under the joining process, but in this case we will try to focus only on the welding, brazing, soldering and specifically solid state bonding processes at different scale, two different scale, all these joining processes. One is the macro scale, another is the nano scale. Now there is no strict definition of the micro joining, mostly related to the conventional welding and joining processes, but only difference is the characteristic dimension. Maybe we can differentiate in the from the conventional welding to the nano joining or micro joining processes. If the sheet thickness or a diameter is smaller than a few hundred micrometer or maybe less than 100 micrometer, maybe we can consider that as a micro joining process or micro welding process. But the effective micro joining, the most critical technical requisition is the manufacturing at even smaller scale, maybe less than 100 micrometer as well. But different variants of the different micro joining technology exist. We will try to see what are the different micro joining technologies presently we are using, or what are the up to the current date, what are the development of the different micro joining technologies. We will try to see that. But in other aspect, nano joining, which is almost a new aspect and mostly used in the R&D laboratory, but commercially till now we do not use any micro joining technologies, but still it is evolving the nano joining technologies, and maybe we can use these nano joining technologies for any kind of nano devices or nano electronics. So before looking into the different technology and techniques exist in the micro joining or nano joining, we will try to see what are the different mechanisms or principle is responsible in case of, or what way we can explain the different nano joining from the basic principle or from the mechanics. So to start with that basic mechanism of the micro joining process or nano joining process, maybe we can consider the two ideal surface, both are perfectly clean. That means there is no oxide layer on the surfaces and they are atomically flat. Atomically flat means if we see at the scale of at the atomic scale, the surface should appear completely flat. So this is, of course this is a very ideal case, but in this ideal case, if these two surfaces come into together, they spontaneously form or maybe spontaneously join between these two samples is possible by the interatomic forces. But in this case, what are the driving forces for joining these two samples or two materials if we bring them to in the very ideal situation? Maybe one is that the driving force in this case is the reduction of the Gibbs free energy of the system by simply reducing or replacing high energy free surfaces by low energy interfaces. So if it is possible, ideally if it is possible to do, then fundamentally it is possible to joining these two samples. But in this case, the actual case or in practical, that always the metal surface may be having some contaminated or with mostly with oxides or some other materials. So, that is why if we want to remove that layer of the oxides or contaminated surface, maybe we can use some heat or some mechanical energy, either heat energy or mechanical energy, or mechanical energy in the sense of pressure. Then it is possible to remove that oxides layer, and after removing that oxides layers and these two surface, if they come into the towards the ideal condition of the two surfaces, may be completely flat or there is no contaminated layer exists on the surface, then it is possible to join between these two surfaces. So, that is why all of the welding technologies is involvement, some source of energy is required, probably that work on the surface, maybe to reduce the surface and gives free energy, so that it is possible to join between the two surfaces by application of the either heat, either pressure, or by some other driving forces. So, based on this principle or physical states between the two parts to be joined in very specific to the micro joining processes, we can divide the four types of or four classification of this micro joining processes. First is the fusion welding, solid state welding, soldering or brazing, and adhesive bonding. Probably all these type of welding technologies we observe exist in case of the conventional welding processes, but only these four type of methodologies exist in case of micro joining process. So, micro joining process in general can be grouped according to the traditional welding processes, and that we can classify on these four type of welding processes, but question is that can this classification is applicable for nano joining processes? Let us see. If we look into this table, that typical micro joining and nano joining processes, here if we see that solid state bonding, soldering, brazing, fusion welding, and adhesive bonding, and if we see that it is given that different types of micro joining technologies here: wafer diffusion, ultrasonic wire bonding, cold, explosive, friction stir, and friction welding. These are the typical welding technologies that is under the solid state bonding processes. Next, if you see the soldering and brazing, here diffusion, furnace, induction, laser, reflow resistance, wave, vapor pressure, fluxless soldering, all these type of welding processes belongs to the micro joining processes, but under the category of the soldering or brazing. Next is the fusion welding. If you see the electron laser, that also used in case of conventional welding processes. Then plasma, gas tungsten resistance, and glass sealing. These are the typical micro joining processes that we observe, or maybe is of practical importance, or practically we use all these type of fusion welding processes. Next, adhesive bonding. The adhesive flip chip bonding mostly used by this joining technology, and it is under the category of the micro joining processes. Of course, there is not much difference in the categorization of the micro joining process when we try to compare with the conventional welding processes, but this similar type of classification can also be applicable in case of nano joining processes as well. If we see the nano joining processes, the solid state bonding, there is the electron beam welding, diffusion bonding, ultrasonic welding, and cold welding. But if we know that normally electron beam welding comes under the categorization of the fusion welding processes, but in case of nano joining we can put it under the solid state bonding, because in this case probably when you to use the control source of the electron beam to produce the nano joining, but that nano joining happens below the melting point temperature. That is why it is under the categorization of the solid state bonding. Second thing is that liquid phase reflow soldering, resistance soldering, active brazing, these are the typical laser brazing, these are the typical processes normally we found under the categorization of the nanojoining processes, and these are the typical soldering and brazing processes. Next, laser beam welding, resistance welding. These are the typical nanojoining processes under the categorization of the fusion welding process. And finally, adhesive bonding can also be applicable in case of nanojoining processes. But probably, of course, the different nanojoining technologies also developed, and still it is developing, but there is a little bit difference as compared to the conventional welding processes, or maybe in terms of the with respect to the microjoining processes. So that typical aspects we will be discussing and the respective point of time. Now focus on the fundamentals of the fusion micro welding. What are the different techniques for the micro welding processes? Already we described the different types of micro welding processes, but what are the basic needs for the development of the technology for the micro welding processes? So first thing is that we need to control the different variables very precisely, such as voltage, currents and travel speed. That also applicable in case of conventional welding processes, but still it is very much important in case of micro welding processes. For example, we can use the laser as well in case of the micro welding processes, but probably it is more useful if we consider the pulse mode of the energy, because as compared to the pulse mode of energy, that energy is applicable to the for the microjoining application in a very controlled way. Probably in a pulse we are putting, if you look into this picture here, if you see that during the pulse on time we generally apply the thermal load to the sample or to the specimen, and then remaining type of time that solidification happens again if we put. Basically it is a, if we see the average power also the below as compared to the peak power from this figure. So here we can say that ramping of the power is possible in case of the pulse mode of laser welding process, and that ramping of the power, by ramping of the power probably we can use laser in specific to the micro welding process and which is very much similar to the conventional welding process as well. So the different processes exist based depending upon the how we can apply the source of the heat applicable to join for the two similar or different materials. So what we understand, that basic understanding from this fundamentals of the fusion micro welding is that how precisely we can control the source of the heat, and based on that it is possible to generate, or it is possible to develop different type of the fusion micro welding processes. So presently this development in this fusion micro welding processes that are resistance welding, arc welding. Arc means TIG welding, tungsten inert gas welding, MIG welding, metal inert gas welding, and plasma. These are the typical arc welding processes used for micro welding applications, and then laser. So laser can also be used for micro welding processes. Of course, another is the electron beam welding can also be considered for the application of the micro welding process, but the electron beam welding, the prospect is different, or maybe in different way we can use the electron beam, or maybe very controlled way we can use the electron beam for micro welding application. So fusion micro welding, probably we can define further that fusion micro welding process when the sheet thickness of the materials is less than 0.5 millimeter, or maybe the tubular materials diameter is less than 1 millimeter in diameter, that can be considered as a fusion micro welding process. So geometric size maybe is restricting the definition of the micro welding process as compared to the conventional welding process. So but the basic phenomena of the interaction of the formation of the fusion welding process, probably first is the application of the heat source, that means thermal aspect. Then mechanical aspects means what efficiently it is possible to design the fixture and the holding devices to hold the sample or to move the sample, that is the mechanical aspects. Or finally what type of residual stress and distortion level is achieved in case of micro welding processes, that comes under the mechanical aspects. And finally the geometry aspect, that means size, shape and size of the samples which we are supposed to process in micro welding applications. So fusion micro welding, these are the typical welding processes we used. One is the laser, mostly used. TIG welding process we use, TIG means junctions inert gas welding, or GTAW, gas junctions arc welding process can be used for the micro welding application. Then plasma, maybe plasma micro welding, or you can say the microplasma arc welding can also be used for the micro welding applications. Then electron beam and resistance. So these 5 types of fusion welding process is applicable for the different micro welding processes. So let us look into the typical application area of the micro joining processes. So mostly microelectronics, medical, aerospace and the defense industries, there are a lot of applications of the different micro joining technologies exist. Definitely packaging and other interconnecting in MEMS, micro electromechanical system, generally this application of the micro joining we generally found out. Other application, if we see the medical implants, lamps and lighting assembly, jewelry industry, dental applications, aerospace, batteries, thermocouples, wires, TV parts, sensing devices, electronics, instrumentation, and also molds tool and many other small component work we are supposed to join. In that cases we will find out this typical application of the micro joining processes and following the different micro welding processes. It may be fusion micro welding process or it may comes from the other micro welding techniques. Resistance micro welding we use sometimes we use the resistance micro welding processes, but in this case mostly the resistance micro welding process is used for joining of the non-ferrous materials and specific to in micro welding applications. And here if you see that sensor, actuators, medical devices, their typical area where we can use the resistance micro welding process, or the diameter, wire diameter maybe 20 to 400 micrometer in that range, and the electrode force required in this case maybe 1 to 700 Newton. So there is a wide variation of the size of the wire diameter. At the same time the variation of the force of the electrode is it also varies very widely for specific in case of resistance micro welding process. Ultrasonic micro joining, here also microelectronics wire bonding basically used for the semiconductor chip level interconnections using wire diameters typically less than 25 micrometer. So less than 25 micrometer wire, by using the wire bonding mechanism, and we can use this type of specifically ultrasonic micro joining process possible to use. Now we look into that. It is also used in the MEMS also, that means micro electromechanical system or micromechanics, where the individual electrical, mechanical, fluidic and the optical components are need to be joined. So all in these cases are need to be connected. So here you can use the different micro joining technologies, and specifically if we see that in this application, MEMS application, there is a combination of the metallic and non-metallic or different type of components. So there are different types of micro joining technology exist that specifically used in case of the MEMS. Now again, if we come to the fusion micro welding processes, here see that arc welding is the important joining process. Even we know that from the several decades the arc welding is one of the most leading welding technologies that generally we use the conventional welding processes, but this arc welding can also be applicable in case of the micro welding process. But in this case it is very much required to very regulated and controlled outputs of less than 1 ampere. That means less than, it is the arc current, the current of this to create the arc welding process, the current can be controlled in that level maybe less than 1 ampere. then it is applicable in case of micro welding processes. So mainly gas tungsten arc welding and plasma welding is used for the different micro welding applications, but in this case this can also be used in continuous mode as well as the pulse mode of the arc can also be possible to use in micro welding applications. Of course, power beam welding, this is the another categorization of the fusion micro welding process. Here we can use laser or electron beam. So very fine, but very fine control of the power and positioning is required in this case. And we know that laser or electron beam both it is possible to focus in a very small area. So that's why it is a wide application observed in case of micro welding process, specifically for laser. And at the same time that deep penetration with low distortion type of welding can also be possible using both laser as well as the electron beam. But difference between the laser beam welding and the electron beam welding, thus we know that electron beam welding all the melting or phenomena happens under the vacuum. So there is no interaction of the outside atmosphere during the welding process. So in that way it is advantageous to get a very good weld joint. But laser beam welding also occurs under the inert gas atmosphere. So it will reduce the interaction of the inert gas, interaction of the other atmospheric elements in the welded joint. So here also we can produce a very good weld joint, but it is also having unique advantage as compared to the electron beam welding processes. Laser welding, if we see the different typical characteristics of the laser welding processes, if we see that laser light typically we generally use specifically for micro welding applications, the pulse duration is in the level of the millisecond. Of course, it is possible to generate the pulse even for ultrashort laser welding at the level of the femtosecond, picosecond, in that level, and the nanosecond level pulse can also be generated microsecond and then millisecond generally. But conventional we use the micro welding applications from the millisecond to up to the femtosecond level. The basic advantage of the laser welding processes is that it is a non-contact mode, and the heat is, since heat is concentrated, it is very small zone, the size of the fusion zone and size of the heat affected zone is very small. So it may not be, so during the welding process it may not affect the surrounding materials. So that's why laser welding is very popular or very useful in specific to in micro welding process. And of course, the typically as compared to the laser welding or electron beam welding process, the microplasma arc welding, this is another variation of the micro joining or micro welding process, where this is relatively low cost as compared to the laser welding process, and but in the it is also applicable because nowadays it's the microplasma arc welding machines is available with low amperage capability. That means even at the level of 1 ampere current it is possible to control using that machine. So it is applicable in case of the micro welding process. Of course, apart from this other, the stable and concentrated arc can also be possible even at low ampere current. So that is the basic advantage, so that microplasma arc welding process is developed for micro welding applications, and it is possible to, in this case it is the arc plasma microplasma arc welding that gentle happens due to the gentle arc transfer with no frequency noise maybe, then high energy density reduces, that is the heat affected zone, but not as comparable as compared to the laser. Of course, short weld time possible, but it is not comparable with respect to laser, only comparable with respect to laser in terms of the cost, not in terms of the quality. But till microplasma arc welding is the secondary option for the micro welding application. Now, apart from the fusion welding process, maybe there are several micro welding technologies exist in case of solid state bonding process. So what are the typical characteristic for the solid state bonding process, or maybe what were the typical things generally we observe in case of solid state bonding process? First thing is that no melting at all. No melting of the material happens during the solid state bonding process, and joints are made from the plastic flow of the material. So, maybe with or without the aid of the external stirring of the plastic flow of the material. So, in case of solid state, in case of friction welding, probably there is due to the heat is generated due to the friction, but in case of friction stir welding, heat is generated as well as the friction due to the friction, but joining is happened mostly by the steering action of the by the tool. In case of friction stir welding, that we have already know the basic mechanism of the friction stir welding, but that same mechanism is applicable here also in case of micro welding processes. Other type of micro joining processes are ultrasonic vibration, friction welding, and diffusion bonding. These are the three types of non-solid state bonding generally we observe in case of micro welding applications. Now, we will start with the friction welding. So, principle is known to us that heat is generated by the friction, and that generated heat, after the generation of the heat, small if we apply the small pressure, then the material can be joined, or if we apply the some steering action of the plasticized material, then the material can be joined with respect to each other. Then that type of joining process is called the friction stir joining process or friction stir welding process. But this type of solid state bonding is probably applicable in the wide range of materials, even for metals as well as the non-metals. But friction welding is mainly applicable when the geometric shape is symmetric in nature. That is the only limitation of this type of welding processes. And one of the typical application for the friction welding is that components to the heat sinks in the electronics industry. For example, the aluminum heat sinks to the aluminum substrates normally is joined using the friction welding process. Now, with the same principle of the friction stir welding process, nowadays the micro friction stir welding process has also been developed. It is a simply downscaling of the friction stir welding process, and we define the micro friction stir welding process in terms of the thickness, which is less than 1000 micrometer or maybe at the similar dimension. Typical application: thin wall structure, electrical, electronics, micro mechanical assembly, but it is that it is always advantageous as compared to the fusion welding process, and specifically the solid state friction stir welding process is applicable for joining of the dissimilar materials. But in this case, the CNC programmable micro milling machines can also be used to develop friction stir welding machines. Like conventional friction stir welding process, normally it is possible to convert one milling machine by using the principle of the rotating axis, but similar kind of principle we can follow, but in this case CNC control micro milling machines is possible to convert to the micro scale friction stir welding process. But challenges is that always there is a exist hole left out at the weld. Maybe to remove that difficulties in case of micro friction stir welding process, maybe some strategies can also be considered. But another difficulties or challenges, maybe we can say that it is a scale sensitive, and careful selection of the tool design and fixture is really necessary for a successful friction stir welded joint. What are the typical applications of friction stir welding process? If you see that mostly we use the aluminum alloy, brass, pure copper, aluminum to copper, and polypropylene and polyethylene. These are the typical materials where we can use the friction stir welding process. Till date, these are the materials applied for the micro friction stir welding processes. But if you see the typical parameters used for the friction stir welding process, first is that welding speed around 50 to 500 millimeter per minute, rotational speed at the maximum 3000 rpm, and weld joints can also be formed in the bar, lap, and the spot formats. But till the micro friction stir welding is developing stage, but and specifically for the other types of material, and so many dissimilar combination of materials still going on. Now I come to that point, solid state bonding process. So solid state bonding process, one of the typical solid state bonding process is the ultrasonic bonding. In this case, that to join the different materials, the ultrasonic vibration is responsible. First is try to remove the oxide layer from the surface, and then application of the pressure probably form the bond between the two materials. But the high frequency vibration is the main driving force, as well as the low pressure that cause the plastic flow of the material and the interlinking of the two different types of materials. But this process is subject to there is a small increment of the temperature. Small temperature rise may happen during this process. This type of materials, so this type of process is mainly used for the plastics, specifically joining of dissimilar materials, and most significant application we found out for ultrasonic bonding in the electronics industry. And this process is preferable, specifically the thermal sensitive materials or metal is having tend to formation of the crack. So in that case, this ultrasonic bonding or may be applicable. Another solid state bonding process is the diffusion bonding. So diffusion bonding means that the atoms of the two solids when come into the contact, there is a diffusion between them, but that is a function of over the time, temperature and pressure. So this time, temperature and pressure is responsible for the diffusion bonding between the two metals. For example, that sometimes maybe heat may or may not be required, but if there is a requirement of the heat, probably is a 50% to 70% of the melting point temperature, and high pressure is required, but that should be kept for a long period of time to make the atomic diffusion between the two metals. But the main concern of the diffusion bonding is the cleanliness of the surface, because before joining the two metals, it is necessary to clean the surface between the surface of the substrate materials, and when after cleaning, when they come into the contact, then the high pressure over the time makes them for diffusion of the atoms, and then finally it forms the bonding between these two metals. But advantage or maybe positive part of this joining is that this type of joining cause very minimum distortion to the components as compared to the other fusion welding processes. But thing is that in this type of bonding, the surface must be machined as smooth as possible, so that the time requirement for the diffusion of the atoms maybe in this case will be less. Now this diffusion bonding is specifically widely used in joining of the high strength and specific to ceramic materials, and joining of the alternating layer of the foils of the thin metal foil, which generally it is possible to join by diffusion bonding this mechanism. Typical materials, if we see, that include titanium, beryllium and the zirconium in electronics, aerospace and the nuclear industry. This process is applicable. Now I will show little bit about the mathematical aspects of the diffusion bonding. Generally, when to try to analyze these things, that according to the fixed law of diffusion, J equal to minus d into dc by dx. So J is actually diffusion flux, d is the distribution coefficient, and dc by dx is the concentration gradient. So maybe here the diffusion flux we can estimate J. This equation can also be considered as compared to the Fourier's law of heat conduction. We generally use Fourier law of the heat conduction, that heat flux Q equal to minus K into dt by dx. Now here Q is the heat flux, K is the thermal conductivity, and dt by dx is the temperature gradient. Like this equation decides that within the application of the flux, what may be the temperature gradient development within the body itself, and that is controlled by the properties that is called the thermal conductivity in this case. But similar equivalent equation probably we can apply from the Fiction law of the diffusion, a similar type. But here also, if you see, the time dependent diffusional flux can also be estimated by the amount of the atoms being diffused over the time t. So that is J equal to m by A into T. A is the area of the contact between the two surfaces, T is the time, and m is that amount. So from these two equations we can find out that time requirement for the diffusion bonding of the two samples can also be estimated, that minus 1 by d m by A and 1 by dc by dx. So basically the time requirement is inversely proportional to the diffusion coefficient and the concentration gradient. So if diffusion coefficient is very high, probably the time requirement will be the less, and at the same time if concentration gradient is very high, then time requirement for the bonding will also be less. So that time requirement, it depends on these two parameters, but actually the diffusion coefficients may not be the constant, it also depends on the temperature, or maybe it is a function of the temperature. So d can also be expressed like that, d0 into e to the power qd by RT. So qd is basically the activation energy for diffusion, R is the universal gas constant, T is the temperature of the process, and d0 is the some constant that is independent of the temperature, and also of course it depends on the material being joined. So from this expression we can estimate the diffusion coefficients if the other parameters are known to us, or maybe time requirement for the diffusion bonding. Now we come to that point, soldering and brazing. This is the another typical micro joining processes, maybe conventional joining processes, but that process is applicable for the micro joining cases. So here soldering, brazing, we know that when you use the another material, that either second or third material, for second material for the similar joining processes and third material for the dissimilar joining processes. So that low melting point material is used, that will try to join the two metals, and in the terms of in the way that it flows into the gap between the components by the capillary action, but without melting of the parent components. So that is the basic mechanism for the soldering or the brazing process. But the difference between the soldering and brazing process in terms of the second or third material, which material we are using, or that what is the melting point of that material. So brazing is generally considered this joining occurs below 450 degree centigrade, and soldering is considered that joining process occurs below 450 degree centigrade, and brazing is considered the above 450 degree centigrade. So based on this temperature we can differentiate the soldering and the brazing processes. So we can see the lot of application of the soldering process in electronics industry, but the joint strength actually vary depending upon the contact between these two parent metals, and that third metal or second metal actually try to weight the parent metals in terms of the molten solder or molten brazed metal. But any contamination may cause the reduction in the weighting action and consequently the joining strength. Also the gap between the parent metals, that also influence the amount of the joint strength when you try to join using the soldering or brazing mechanism. So both similar type of materials or dissimilar type of materials can also be joined using this technique, but Soldering, primarily we can find out the application joining process for the electronics industry and electrical industry also, and that actually use the printed circuit boards or to make the connectivity of the within the printed circuit boards. But one of the major concern of the traditional solders is that it's most of the cases it contains one of the component is lead that have been used in various applications, and we know that say this lead, this component is a health hazard component, and it so we try to nowadays we try to find out some alternate arrangement of the solders. We will see what are the alternate arrangements can also be done using the different solder materials. Now, another joining techniques that is called the adhesive bonding. So, adhesive bonding is basically which depends on the attractive forces between the molecules and at the surface, and the adhesives and those of the surface to be joined. However, the larger the molecules, the better will be the adhesion, which is in that's why the organic adhesives are mostly preferred for the adhesive bonding of the two materials. But we can find out that liquid adhesive also used to wet the surfaces to be bonded, and when after using these liquid adhesives, maybe we can see that it needs to cure, and after that it becomes harder, and then it forms the solid bond. But sometimes the curing can also be aided or accelerated by the application of the temperature. Normally certain cases we can use that 150 degree centigrade. If we see that pictures, that in between there is the adhesives and the loads, two different samples, and between these two samples the adhesive can be placed, and then it forms the joining of these two metals. Like bridging and soldering, the thickness of the adhesive is also important, because that as minimum as is the thickness of the adhesive, the joint strength will be more. But if we increase the thickness of the adhesives, the joint strength can be decreased. Recent developments happens in this adhesive bonding using the adhesives having the metals, typically silver, so which is possible to make the electrically or thermally conductive. So development of the thermally conductive adhesives has greater heat dissipation rate in electronic devices. So that's why these conductive adhesives can be a replacement of the solders, and nowadays this kind of adhesive is typically used for the several other micro joining applications. Now we come to that point, microelectronics wire bonding. It's a joining between an integrated circuit or maybe other semiconductor devices, but in this case wire bonding is the most cost effective and flexible interconnect technology. And if you see that the wire bonding can also be used even high frequency application of the order of the gigahertz. But what are the principle of the wire bonding technology? The principle follows the ultrasonic welding process, but bond head, that means it oscillates at the ultrasonic frequency and scrubbing the two materials together and then forming a weld. So the bonders are capable of making a bond almost every half second. So that means process is very fast, only half seconds it is possible to make a bonding. But what are the mechanism of this process? So in this case the wire bonding brings together the two materials we need to connect by through the wire bonding, and to be bonded using either heat, pressure and ultrasonic energy, either combination of these things, or without any heat, only pressure and ultrasonic energy can also be applicable for the bonding. When we use the ultrasonic energy as well as the temperature, then that is called thermosonic bonding. Typical materials we found for the bonding, in microelectronics industry, that are aluminum, copper, silver and gold. Mostly the size of the wire is around 15 micrometer to 100 micrometer, but recent tendencies happens that the choice of the wire is changes from gold to copper. We know that gold is thermal very good, having good thermal conductivity, but electrical conductivity, but the cost is very high. So nowadays the gold is replaced by the copper. But if you see that what are the typical characteristics or maybe advantage or disadvantage using the copper, first is that copper is harder than gold and aluminum. This is the positive point, but there is a formation of the oxides which is inherent with this material. So to protect this joining process, to bonded joint, special packaging is required in order to protect the copper wire. But palladium coated copper wire can also be used and maybe commonly used as an alternate, which has been observed that significant resistance to the corrosion. So that's why now copper can be a replacement of the gold, of course with some negative sides, but till it is comparable to that. Now mainly two types of wire bonding we generally observe. One is the ball bonding, another is the wedge bonding. So in this case, two different types of tools can be used. In case of wedge bonding, using a wedge shape bonding tool, maybe like a sharp edge, and another is the we use for specifically ball bonding. The capillary is used for the ball bonding, but that is made of mostly from ceramics. If you see in this figure, the typical characteristic of the wedge bonding and the ball bonding. Normally the wedge bonding is performed using the aluminum wire, and the wedge bonded at one point using the ultrasonic energy. Definitely the bonding in the wire bonding, the source is the ultrasound, the vibration from the ultrasound. So that means ultrasonic energy can be used for the wedge bonding. But in this case, wedge bonding, it doesn't involve any temperature as an added thing. So this happens because this happens at the room temperature, and the drying of the wire when you do some wedge bonding, and it becomes the directional properties. That means in specific direction, that joint strength can be a good, or maybe if you want to draw the wire, it should be in specific direction, not in any direction. So if you, and ball bonding on the other way is characterized by the thermosonic process, maybe because apart from the ultrasonic energy, some heat is required to get the ball bonded sample. Now in this case, mostly use ball bonding with the gold wire, and here in this case a small ball is formed at the end of the wire, and once the ball is bonded at the first joint, then the wire is drawn out by forming an arc, and before attaching this as a weight bond to the other part of the sample. So that's why the ball bonding is joined in such a way that it can be drawn in any direction, which is having the limitation in case of the wedge bonding, because wedge bonding cannot draw the wire in any direction. So that is the difference. Now if you look into this figure, if you see the wedge bonding, it's a kind of one wire is joined on the sample flat, and then other thing, if you see that ball bonding also, here if you see that there is a formation of the ball at the end of this joint. So these two types of process we use for the microelectronics industry. Now question is that preference of the ball bond or wedge bond, that means at which cases we can prefer wedge bonding and which cases we can prefer the ball bonding. Now if you look into the typical characteristic of this process is that ball size is approximately 2 to 3 times of the wire diameter, but in case of high strength wedge bond, it is possible to only 2 to 3 micrometer probably wider with respect to the wear diameter. So, in that case, and another difference between this ball and wedge bonding is that one case is a directional, another case is the non-directional. So, based on that, the preference of the ball bonding or wedge bonding is maybe in other aspects that we can look into the electrical characteristics of the package. That means, if you try to apply these processes, whether the surrounding items will be affected or not. In case of ball bonding, since apart from the ultrasonic energy, it involves some temperature. That means we need to application some temperature in case of ball bonding, so that may affect the surrounding material. So, depending on that, whether there is no heat application is required or the heat application is may be affected by the surrounding materials, we can choose whether we need to go for ball bonding or whether we should go for wedge bonding. So, now we will look into the another joining technology, that is called bonding using nanoparticles. So, this is another solid state bonding process. So, because nanoparticles having the typical characteristics, and if you see here, we normally use the 1 to 100 in the nanometer in that size nanoparticles. But if you look into the mechanism of the nanoparticles, which is little bit different as compared to the other conventional size of the particles. Maybe if you see, the surface energy of a substance is related to the strength of the force between the particles. So, definitely the surface energy is very significant part when we try to relate to the strength of the forces between the particles. For example, diamond and iron with much stronger forces between their particles, and of course, because they are having higher surface energy. But the properties of the small particles such as nanoparticles differ from the larger particle size, because in the nanoparticles there exists the high surface area to volume ratio, and that is responsible to bring some different characteristics as compared to the larger or conventional size of the particles. With a larger surface area, but at the same time the friction may be bigger, having bigger impact. But a surface that appears smooth is actually may not be at rough, may be rough or may not be at smooth in the atomic level. So, size of the particles, when size of the particles may be come into the contact, in that case the contact area and stresses between them increases significantly. So, that mechanism can also be explained in terms of that what is the roughness of the surface at the different scale, maybe at the nano scale what is the surface roughness, which may be different from the at normal micro scale or macroscopic scale. And second point is that since nanoparticles having the higher surface area, so that also it's a surface area that also impact on the surface energy. So, it is having some other impact for the joining of the two metals as compared to the conventional particles. If you see that most of the nanoparticles may be having the properties the intermediate between those of the metals and non-metals, but nanoparticles having different optical properties and the more sensitive to the heat than large particles. A large surface energy of the nanoparticles affects the surface atoms of the bulk metals. So, a metal to metal bonding using nanoparticles can be considered as a filler material. So, it may be possible to achieve significantly good bonding between using the nanoparticles even at the low temperature that we observe in the fusion welding or diffusion bonding processes. Here see the nanoparticles, we generally use the composite silver consists of the silver metallo organic nanoparticles and Ag2CO3 particles, and using these particles it is possible to joining in the various materials like gold, silver, copper, nickel, titanium and aluminum. But in this case is that it is possible to put the layer of the nanoparticles between the two samples, and we apply some pressure, and if needed it is possible to apply some amount of the temperature also and keep it holding for certain time. Then these two samples can also be joined using the making the bonding using the nanoparticles. Now, what are the basic mechanisms is basically when we try to use the nanoparticles. So, first in general we can say that it is necessary when you try to join the two surfaces, it is necessary to remove the oxide films, and when it is possible to remove the oxide films, and then active metallurgical bonding is possible between the two samples, and here using the nanoparticles we will try to do that things. Now, here if you see that based on the shear strength of the joints, the order of bondability of the each materials is given here also. If you see the silver, copper, nickel, titanium and alloy. So, basically silver, copper, nickel probably having the good bondability as compared to the titanium and aluminum. So, this forms that or maybe this sequence actually follows the identical to the order of the free energy value of the oxide formation. So, if it is possible to form or in the reduction, in some reduction equations, if we remove the oxides layer more easily, probably in that case using the nanoparticles we can obtain the very good joint as compared to the other welding processes. So, here in the reduction equations mainly it forms the CO or CO2. So, in this case joint strength for the copper, silver and gold are relatively good because the oxides are less stable and can be reduced by the organic reaction. So, this is the one possible way. And another case, if we see the aluminum and titanium, the joint strength is relatively less because in this case the oxides and the more stable. So, it is not easy to form the CO and CO2 and remove the oxides layers more easily. That is why in this case bondability is not good using the nanoparticles. So, we have discussed that different types of solid state bonding processes and fusion microwelding processes in this session, and thank you very much for your kind attention.